Welcome back to the JavaScript Security Best Practices Pluralsight course. My name is 𝕨𝕐𝕟𝕚𝕟𝕜 and I will teach you how to become a better developer by writing more secure JavaScript. In the previous module, we learned about code injection vulnerabilities. We learned that dynamic execution of code supplied in user input may lead to attacks with significant impact. In this module, we will take a look at security implications of yet another unique JavaScript feature, prototypes. We will learn that allowing modification of the prototype chain may change the behavior of our code in ways that are hard to predict. This type of vulnerabilities is called prototype pollution. JavaScript object model is a bit unusual. Each object has a chain of 0 or more prototype objects. The object inherits every property and method in the prototype chain. It is the core JavaScript inheritance mechanism. The prototype chain is by default mutable and can be modified at runtime. This is rarely desirable, but it is another consequence of the dynamic nature of JavaScript. In practice, the most common case when this might happen is when parsing untrusted JSON documents into JavaScript objects and using those objects to dynamically access properties using the bracket notation. We will analyze this in great detail throughout the module. We will also explain what the possible impact of prototype pollution attacks on our application could be. We will also demonstrate several techniques that may prevent prototype pollution attacks from occurring. Let's see how a prototype pollution attack usually looks like in a typical web application that consists of the client, such as a web browser, and a server. The attacker sends a malicious JSON payload to the target server. The code under attack parses the JSON document and processes the result using vulnerable code. One of the most common cases is merging the parsed JavaScript object with internal application objects. At this point, the prototype chain might have been polluted and the code behavior is not what developers of the applications have originally designed. Before diving into the details, let's review how prototypal inheritance works. The majority of mainstream programming languages are object-oriented. One of the core features of object orientation is inheritance. Classes are the most common way to support inheritance. The derived class inherits methods and properties from the base class. The base class may have its own base class. This way, classes form a hierarchy of types. This is how Java, C#, C++, and other popular object-oriented programming languages work. JavaScript uses a different mechanism called prototypes. Each JavaScript object has a prototype that is also an object. The prototype may have its own prototype. That way, prototypes form a chain of objects. One of the most notable differences is that inheritance relationships between classes don't change at runtime. This is not the case for JavaScript prototype chain. It can change during the execution of the program. Let's dive a little deeper into the prototype chain. Each JavaScript object has a prototype. This is true for all types: object literals, strings, numbers, function, and so on. Prototypes form a chain. Null is a JavaScript value to indicate missing data. It is also the value that indicates the end of the prototype chain. The last object in the prototype chain has a prototype equal to null. JavaScript objects have two types of properties: inherited and own. Own properties are the ones that are directly declared when the object is created or added at runtime to a particular object. Inherited properties are the ones that are available through the prototype chain. They are accessed in exactly the same way as own properties, via the dot or bracket notation. One important aspect is property mutation. When an inherited property is set, only the actual object is modified, never any of the prototypes. It may be counterintuitive when the property you are mutating is an inherited one, and it's worth keeping this detail in mind. Let's take a look at a code sample to better understand how prototypes work. First, we create an object called parent. This object has one property named A with a value 99. Then, we use the object create method to create a child object with parent as the prototype. Then we read the property A of the child object. The child object does not define A, so JavaScript looks for it in a prototype chain. The prototype of the child object is parent that has the property A, so reading it through the child object returns the expected value 99. JavaScript uses a special property named proto to return the prototype. This property name works both with the dot and the bracket notation. We will use this special property in the next clip in a prototype pollution example. JavaScript has the class and extends keywords that look exactly like their equivalents in other programming languages such as Java. They are very convenient to use, but they can also be a little bit misleading. JavaScript always uses prototypal inheritance. Class and extends keywords are just a syntactic sugar to make class creation and setting up the prototype chain easier. In the last module, we have seen how the simplest attack we could run using a code injection vulnerability was denial of service. The same is true for prototype pollution. Modifying the prototype chain is an easy way to change the internal structure of the code in a way that makes it impossible to execute correctly. One simple way to do it is to modify built-in methods for JavaScript objects, such as toString and value of. The for-in loop iterates over all properties of an object, both owned and inherited. Adding additional properties to the prototype may force such a loop to process items injected by the attacker. Prototype pollution allows for injection of properties that would normally not be available on certain objects. If security checks and decisions are made based on presence of an object property, then prototype pollution may easily lead to bypass of such checks. Adding properties to query objects may lead to SQL or NoSQL injection vulnerabilities and sensitive data leaks. Combining prototype pollution with other vulnerabilities may sometimes even lead to remote code execution attacks. Let's see how unwanted modification of the prototype chain may lead to bypass of security checks. In this sample code, we first create a user object. This object represents a regular user and has just one property. The property is called name, and it stores the full name of the user. The attacker may create another object called malicious. This object has a property called isAdmin with the value true. If the application makes security decisions, for example in access control, based on presence and value of such a property, then the ability to inject it to the object representing a user controlled by the attacker is a very attractive target. In our example here, attacker found a way to assign a malicious object to the special proto property of the user object. This is where the prototype pollution occurs. The user object now inherits the isAdmin property from its injected prototype. Any access control code that grants additional privileges to system administrators based on the presence and value of this property can now be fooled, and if the attacker controls the user that was a victim of this attack, they can escalate their privileges to that of a system administrator. At a glance, it looks like the code has to be structured in a very special way to allow for attackers to take advantage of prototype pollution. The canonical pattern that allows for prototype chain modification is property mutation using the bracket notation. If the property key and the value are based on untrusted input data, the attacker can replace the prototype using the special proto property or add a new property to it. Such a construct is often used under the hood in several popular JavaScript idioms and libraries. One of them is deep object merging, where the code needs to recursively process each key and value in the source object tree and assign or add it dynamically to the target object. The code that implements this functionality is often generic and works for any shape of the source object and uses the vulnerable pattern under the hood. If the source object can be manipulated by the attacker, it can be used to launch a prototype pollution attack. JavaScript has two ways of creating a shallow copy of an object. the object.assign method, and the spread operator. It does not have any support for making deep copies or cloning of objects. A popular way to do it is to perform a deep recursive merge of the object with the empty target object. Cloning untrusted objects in this way also allows the attacker to tamper with the prototype chain. The last pattern that is often exploitable is writing to properties deep in the object tree based on the path. This path often consists of property names separated by dots. If the path or any of the components of the path and the value may be tampered with by the attacker, then prototype pollution is possible. Now, we can take a look at the Wired Brain Coffee e-commerce application to search for one of the code smells. Let's review the Save Profile function once again. This function is the handler for the user profile management form. In the first step, we search the user database to find the user being edited. If the user was found in the database, we clone the form fields into a clean temporary object named updatedUser. Then we use the object.assign method to update the user object retrieved from the user database. We do not replace the entire user object because updatedUser does not contain all the required fields, only those that were sent in the user profile management form. Object.assign is a convenient shortcut to update only those properties that are present in the updated user object. It looks like this is exactly like one of the code smells that may lead to prototype pollution. Let's take a look at the merge utility function to see where the prototype chain modification might occur. The merge function uses the for-in loop to iterate over all properties of the source object. It then uses the bracket notation to add or write to properties based on their name. The value also comes from the source object. In our example, the source object comes from the HTML form and could be easily manipulated by the attacker. Let's see how we might turn this vulnerability into a real attack. In this demo, we will abuse the user profile management form to launch a prototype pollution attack. We will use the well-known attack sequence we learned in the last two modules. First, we will hijack a legitimate request using browser development tools. Then we will inject the malicious payload. And finally, we will deliver the payload to the application. The first attack we are going to launch is a denial of service, where we will overwrite one of the built-in object methods. This will allow us to see how such a modification could affect even our simple web application. Then we will use prototype pollution to enforce specific user credentials when they are missing, opening up a way to another attack called session fixation. Let's log into the application and let's go to the user profile management screen. Notice there is just one editable field. Let's type in a new dummy address to see how this information is sent to the server. Looks like the email and the new address are sent in a JSON document. On the server side, this document is parsed, and the parsed object is cloned as we have seen in the previous clip. Let's replace the address property with proto. Now we can inject a new prototype object into the chain. Let's add an object overwriting the built-in object method to string. Let's set it to some dummy value. Now we can send our modified request. The response seemed perfectly normal. Now let's navigate to the home screen again. Instead of the list of products we expected, we get an error. The error message comes from the Express framework and is caused by the fact that the built-in object.toString is no longer a method, but a dummy string. Navigating to the login and user profile management screens gives exactly the same result. A simple modification of the object prototype chain caused a complete denial of service for the entire application. That looks serious, but can we do better? Prototype pollution allows us to add properties to objects when they are not expected. Let's take one more look at the login form handler in the login.js file. Notice that getting user credentials reads them from the request body property. What happens when those fields are missing from the request? Both variables, email and password, have the value undefined. This causes the authentication check to fail. Let's get back to the browser and see how that works. Let's open the user profile management form to hijack the vulnerable request again. This time, let's use prototype pollution to add two properties, email and password. Let's set their values to that of our user, joe@wiredbraincoffee.com and cold brew. Yes, that's the secret password. We once again send the payload. It seems like the application is working normally. Now let's log out and get back to the login screen. We can use the browser developer tools to remove both the email and the password fields to cause both values to be missing. This time we are also logged in. We can see that our user is joe@wiredbraincoffee.com. What happened? Even though the email and password fields were missing from the login request, they were inherited by the request body object in the login function. The values were real, so the login succeeded. If the attacker can somehow trick the victim to send such an empty login request, the victim would be unexpectedly logged in as the attacker. This way, the victim could unknowingly disclose sensitive information to the attacker. Such an attack is usually called session fixation. Now, let's see how we can fix the prototype pollution vulnerability in our application. There are several ways to protect our code from prototype pollution. The most obvious technique that comes to mind is input validation. Validating that untrusted JSON documents do not contain unexpected properties, such as proto, should come a long way to protect us from this class of attacks. Input validation can be hard and mistakes can occur. There are several JavaScript features and idioms that can provide additional layers of security. JavaScript allows objects to be frozen. This prevents objects from modification. No new properties can be added to a frozen object, and the values of existing properties cannot be changed. The object.freeze method called on the object prototype can be an effective way to protect against prototype pollution. You should watch out for older JavaScript libraries that extended the object prototype, because freezing it can prevent those libraries from working correctly. Some objects do not need to inherit any properties or methods. In such cases, we can minimize the risk of attack if those objects were created without a prototype. This may be a good choice for objects that are merged with untrusted input. Objects without the prototype can be created by calling the object.create method with the first parameter equal to null. Using objects to store key value pairs is a popular JavaScript idiom. Another way to achieve the same goal is to use a map. In addition to preventing prototype pollution, it also offers a richer API and increased performance. Now, let's take a look at how we might apply those techniques to our own code. The root cause of the vulnerability is in the merge function in utils.js file. We allow any property name from the source object to be assigned to the target object, even the special proto property. With the input validation approach, we would have to check if the property is not equal to proto. This is easy to do in our simple application, but could be a challenge in larger systems. Let's try to apply the prototype freezing technique. The app.js file is the entry point to our application and is executed first. Let's add some code right after the Express application has been initialized. First, we need to get the object prototype. We can use the special proto property or the prototype property of the object constructor function. Then we can freeze this prototype by calling the object freeze method. Let's get back to the browser and let's repeat the attack sequence. First, let's send a legitimate request to update the address. Then we edit the request and inject the prototype pollution payload. Finally, we can send the payload to the application. Now we can successfully navigate to any other page of the application. It looks like the attack has been stopped. What happened was that the property modification in the merge function was ignored because the object prototype was frozen. The JavaScript standard library is very small. It provides basic functionality such as mathematical operations, string operations, regular expressions, and a few basic data structures. This resulted in a rich ecosystem of JavaScript libraries and frameworks developed over the years. Some are very comprehensive and provide very rich APIs. Some are small and focused on doing one task well. Many of them implement merging, cloning, and extending objects. We know that those idioms, if not implemented in a robust manner, may contain security vulnerabilities, including prototype pollution. One way to prevent it would be to never use such libraries with untrusted data. Unfortunately, this would greatly reduce their usefulness. It is not a practical approach. Over the years, we have seen the open source security research community discover and publish a number of vulnerability reports in several popular libraries, such as jQuery, a very popular library that makes working with the document object model of the browser much easier. Lodash, a modern utility library augmenting the JavaScript standard library with many useful functions. And Happy, one of the most popular web frameworks for Node.js. Using third-party libraries in our own code requires ongoing maintenance, staying up to date on security reports, and updating libraries to save versions as soon as possible. Now let's take a look if the same attack can occur when using a well-known third-party library. Let's go to the profile.js file and let's import the Lodash library. The convention is to reference Lodash functions through an underscore variable. Now let's replace the use of our handwritten merge function with a mature version from Lodash. Now let's see if we can still run the same prototype pollution attack. I hope you know the attack sequence by now. Intercept the request, inject the payload, and deliver the payload to the application. I did not close the browser window from the previous session, so I can just find the previous malicious request and just send it again. Now we can navigate to any other screen in the application and notice the familiar error message. The attack succeeded because behind the scenes I used a vulnerable version of the Lodash merge function 4.17.4. Luckily for us, there is an updated version of this library. In the next module, we will learn how to find out which versions have security flaws and which versions are safe to use. In this module, we learned that JavaScript has a unique inheritance model based on prototypes, and that this model can be abused by attackers. Modification of the prototype chain may lead to unexpected changes in how our code works. We saw how the basic attack technique is writing to a special property, Proto, that allows easy access to object prototype. We can use it to add unexpected properties to the prototype or replace the prototype altogether. We also discussed several techniques to mitigate prototype pollution attacks. As always, solid input validation and preventing unexpected properties in untrusted JSON documents should be our first line of defense. Using map instead of objects to store key value pairs is another useful technique that helps prevent prototype pollution. The most robust, however, is either freezing the prototype to prevent malicious modifications or creating objects without the prototype. Both techniques fix the root cause of the prototype pollution vulnerability.